Okay, so let's start with a pretty simple one. 4.5. It says, in a study designed to gauge married women's participation in the workplace today, the data provided in the file, which I have in the spreadsheet here, were obtained from a sample of 750 randomly selected married women. Consider a woman selected at random from this sample in answering the following questions. And then it wants to know what's the probability that this woman has a job outside the home, the probability that she has at least one child, the probability that she has a full-time job and no more than one child, the probability that she has a part-time job or at least one child but not both. Okay, and the explanatory comments, if you didn't notice, you just hover over the red triangle there. It tells you the coding. Of course, that's pretty obvious for number of children. For job status, we're looking at full-time, part-time, or no job outside the home. Okay, so what we could do is get counts. Right? So part A says, what is the probability that a randomly chosen woman has a job outside the home? Well, we'd want a count of the F's and the counts of the P's. So I could do something like this. So there's my F's and my P's. Count F, B3, 753, P. Alright, then I add those up, equals sum of these. And the probability is simply that divided by the total n, which is 750. Okay, so could do it like that. And that's actually not that hard, but let me show you a much easier way we could do all of this stuff. I'm going to select all the range. Much easier way to select this range is just select the corner, scroll up, shift, select that. Okay, whoop, there we go. And let's make this a pivot table. Let's put it in the worksheet right here. Okay, now what do I want in there? And I want all this stuff in there. I'm going to put, I think I'm going to put job status in rows. I'm going to put number of children in columns, and I'm going to put woman in values, and I'm just going to do a count of the woman because these are just the numbers over here are just numbers in the order that they answered the survey or whatever. So, okay, I think that's all I need. And now what I can do is on part A, I can just say this. What is the probability that the woman has a job outside the home? Probability job out of home. And that is going to be equal to the probability of F plus the probability of P, full-time and part-time jobs. So the value there is probability of F, which is 307, divided by 750, plus the probability of P, which is going to be 178, divided by 750. And notice when I select these cells, it gives a whole string of pivot table, but I think it will grab the value and do the calculation based on the value. And yes, indeed it will. I missed a in parentheses there, which Excel fixed for me. So I want to express that as a percent. I'll just do a formatting change. And voila. And just notice I'll quickly scroll down. And that's what I got down here. But the pivot table is so much faster, and given that I'm going to be doing a few more of those similar kind of probability calculations, I'll stick with the pivot table. And let's put this as a percent with one decimal place. There we go. Okay, so B. What is the probability that this woman has at least one child? So probability at least one child is going to equal probability of one child plus probability of two children. And we don't have any more than that, so we can stop there. And that is going to equal, so here's the total number with one child, it's 271, divided by the total, And the probability of 2 children, 326, divided by the total. And I think I did the same kind of mistake there. Excel's so nice to me though, it fixes my mistakes. And I've got 79.6%. Let's keep going. What is the probability that this woman has a full-time job and no more than one child? It's probability of full-time job and 0 or 1. That's going to be the probability of full and 0, which is 98, plus the probability of full and 1, which is 126. So the probability of full 0 plus probability of full 1. And let's jump down here and calculate that. So it's full and 0, 98, divided by the total, 750, plus full and 1, 126, divided by the total. Finally figured my parentheses out there without Excel correcting me. And we'll put that in the same format, 29.9. Okay, so D. What is the probability that this woman has a part-time job or at least one child, but not both? So probability part-time job or probability of 1 or 2 children, but not both. So we want to look at those individually, but not at the overlap. So part-time job, what we're going to be looking at is the part-time job without any children, 39. So that's the part-time job thing, or at least one child. So we'll look at one child plus two children. Actually, look at these 4 up here. So here's the non-part-time job and at least one child. Here's the part-time job and no children. So I'm basically, and I think this time what I'll do is I'll add this one plus these 4 and then divide that by the sum. So let's just do that and it'll be straightforward. Equals, let's do this, equals sum of 39 and then those 4, that range. You can do this, you can do an individual cell and a range with the sum function. And then we're going to divide that by 750. And we got 66.3%. Okay, so moving on to problem 410. A fair coin, i.e. heads and tails are equally likely, is tossed 3 times. Let x be the number of heads observed in 3 tosses of this fair coin. A, find the probability distribution of x. So we're going to create a probability distribution here first off, and then we're going to use that additive property to find the kind of cumulative probabilities of a few different outcomes. And then we're going to find the expected value and standard deviation, which are measures of central tendency we're familiar with numerical variables, but we can apply the same concepts to probability distributions. So let's just set this up here, A, and I'm just going to do it like this. I'm going to put x as the number of heads and p as the probability. I'm just going to make a little table. Let's underline, let's format that a little bit. And what are the possibilities for x? Well, we could have no heads, we could have tails, tails, tails. We could have one head, and there's a few different ways to get that, right? It's tails. It could be heads, tails, 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 heads, tails, or tails, tails, heads. So that would be 3 possibilities, and then we could have 2. That could be heads, heads, tails, or tails, heads, heads, or heads, tails, heads. And then finally we could have 3, heads, heads, heads. Okay, those are all the possible outcomes. Okay, and I happen to know just by counting in my mind that there's 8 possible outcomes, and there's only one way to get the 0 heads. That's tails, tails, tails. So that the probability there is 1 out of 8. I happen to know that there's let's see, 3 ways to get one head. There could be head, tails, 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 head, tails, or tails, tails, head. So probability of that is 3 out of the 8 total. I'm going to prove this to you here in just a second. How many ways to get 2 heads? It could be heads, heads, tails. It could be tails, heads, heads, or heads, tails, heads. So that's also 3. 3 divided by 8. Then how many ways to get 3 heads? There's only one. That's heads, 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 right? So that's also 1 out of 8 equals 1 out of 8. So there's my probability distribution. Let's make sure those add to 1 because those are exhaustive events. And sure enough. Okay, so I'm in good shape. Now, just in case I lost you there, let me just do something called a tree diagram to prove to you the intuition behind what I just said. So I'm going to basically diagram the flips. Here's flip 1, and it can be heads or tails. Okay, and then on the second flip, based on what it was on the first flip, it's going to be able to become heads or tails again. That's the second flip. And then on the third flip, once again, each one of these outcomes could branch off and be heads or tails again. So I could do heads, tails, like that for the third flip. Okay, now I just want to basically count what are the ways to get first off 0 heads. Well, there's only one way, tails, tails, tails. Okay, and then what are the ways to get 1 head? Let's see. I could get heads, tails, tails. I could get tails, tails, heads. I get tails, heads, tails. Okay, so there's 3 ways to get 1 head. And notice by the way that I've got 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. Okay. How many ways to get 2 heads? Let's do purple. That could be heads, tails, heads. That could be tails, heads, heads. Okay, so that's 2, and then heads, heads, tails. Okay, and then how many ways to get 3 heads? Well, as we talked about, that's just 1. That's right here, heads, heads, heads. Okay, and now I've covered all my possibilities. Okay, I've got my probability distribution set up correctly. Okay, so there's a probability distribution now. What's the probability that 2 or fewer heads are observed in 3 tosses? 2 or fewer. That's going to be the cumulative probability of all of these outcomes. So we're just going to add up those outcomes. Okay, so probability of we're really saying x is, I'll use a proper symbol here. We're saying what's the probability that x is less than or equal to 2? As I mentioned, we could have 2, 1, or 0, and that's the sum of those probabilities. So that's just, I'm just going to do it this way. I'm going to say sum of these 3 probabilities, and it's 0.875. Okay, that's B, by the way. C, find the probability that at least 1 head is observed in 3 tosses. Okay, now for that one, so that's the probability I'm looking for greater than or equal to 1. And of course I could say that's probability, that's this outcome plus this outcome plus this outcome. So I could add these probabilities. Or another thing I could do is say that's really the complement of this outcome. So I could say it's 1 minus the probability of x equals 0. That would be equivalent to the probability of 1 minus the probability of x equals 0. So I could go ahead and calculate that. So I say equals 1 minus that probability. Either way, I'm going to get the same answer. And if I just do it as a sum of these 3, that's going to be the same. Okay. I'm just showing you the application of that complement rule. Okay, then D, find the expected value of x. Now, do that. One way to do that would be just add a third column over here and put weighted value. And that would equal this times its probability, each outcome times its probability. Drag those down, and then sum those up. Just like I did in our expected grade example, you remember, in the lecture portion of this. Okay, so it would be 1.5. Now, that was pretty easy to do with, let's say e of x, expected value of x, equals 1.5. It's pretty easy to do here with a pretty small distribution, but another way to do it, in a way that might be more more efficient with a larger distribution. So I'll show you different ways with the sum product formula. Sum product, and notice what it says here. It says returns the sum of the products of corresponding ranges or arrays. So I select my array, first my possible values, and then my probabilities. What it's going to do is multiply each cell times the equivalent cell in the next array. So it's going to multiply B4 times C4, and then it's add that to B5 times C5 plus B6 times C6 plus B7 times C7. And look, that's the same thing. Okay, that's a little bit quicker way, especially with a longer distribution, to achieve the same result. Okay, so there is my, let me move that up. There is my distribution, or my expected value. And by the way, let me note that this is also expected value of x is the same thing as the mean of the probability distribution of x. Okay. It's the same thing as the mean, or the average. And the reason we're going to need that is because the next thing we're going to do is calculate the standard deviation. But before we can calculate the standard deviation is the square root of variance. So I want to calculate the variance of x. And then I'll take the square root of that to calculate the standard deviation. Now, what is the variance? Okay, so you'll recall that for just a plain old numerical variable like we've worked with before, variance is defined as the sum of squared deviations from the mean. So we would take the xi minus average x, or the mean, squared. And then that would be divided by n or n minus 1, depending on whether we're dealing with sample or population. Now, it's going to be similar for a probability distribution. Okay, so the variance, so this is for a numerical, let's say a numerical distribution of just a variable, a discrete variable. Now we're talking for probability distribution. Okay. And really the only difference, we're still going to have the sum of squared deviations. So I'll say of the xi's minus, now the mean is the expected value, the probability weighted expected value of x squared, and instead of divided by n to average it out, we're going to now multiply it times each probability of each xi. Okay, so it's going to be a little tedious, in fact a lot tedious, but I want to show you how to do that. And then you realize that's really tedious, I'll show you a shortcut, but I want to prove to you that this works. So I've set up 3 new columns here. Okay, first off, I need it's the sum of the squared deviations from mean. So for each outcome, 0, 1, 2, or 3 heads, I'm going to calculate the deviation from mean. That's pretty easy. I'm just going to take that value minus the mean, the expected value, but no, I'm going to lock the expected value in so I can slide this formula down. Okay, so there's my deviations for mean. Now, remember, we have to square those so they're all positive. So let's just do that by multiplying each one times itself. Okay, so there's my squared deviations. Those are my squared deviations. Now to average them, as it were, I'm going to multiply them times the probability weight instead of dividing them by n. So now I'm going to take each one times its p-value. And we'll again drag that down. Okay, now here's my probability weighted squared deviations, and all I need to do now is add them up, and I've got my variance. So I can label this here variance. Let's format. And that's the sum of the probability weighted squared deviations from the mean equals 0.75. Okay, for only 4 possible outcomes, that was a little tedious. Let me show you a cool little shortcut, and this has to do with some math that we don't need to get into. Just take my word for it, or the textbook's word for it. But the math here is that, I'll just show you. We won't prove it, but I'll show you. The math is that this formula here for probability distribution variance can be restated in this form. Variance equals the sum of the observations, so the x, I'll call them the xi's, squared, times the probabilities, so probability of each xi of each outcome, minus the mean or the expected value of x, squared, minus the squared mean. So this converts algebraically to this. And the nice thing about this formula here is that we can use sum product to pretty easily calculate it. So that's what I'm going to do down here. I'm going to do a sum product. And my first array is the observations. That's the xi's. I'm going to square them, so I'm multiplying them by themselves. So I've got that array twice. And then I'm going to multiply them by the probability weights. And I'm done with my sum product. And then all that's left to do is subtract the mean, the expected value here, squared. And to square it in the formula, I put the little caret, which is shift 6 and second power. Hey, what do you know? That is the same as the way I calculated the variance the quote old-fashioned way. Let's highlight them. Let's use green. Okay, so you see that shortcut for calculating variance is just as good. And all you do is kind of plug and chug with that. Of course, we really don't want variance per se. We really want standard deviation, but that's easy. Standard deviation, let me put a label in over here. Standard deviation, standard dev is just equal to the square root of the variance. So our standard deviation, 0.866. Okay, moving on now to problem 418. This is where things get pretty interesting, a little tricky, but actually pretty not too hard if you follow carefully. I'll try to do this as cleanly as possible. So the problem says a quality inspector picks a sample of 15 items at random from a manufacturing process known to produce 10% defective items. Let X be the number of defective items found in the random sample of 15 items. Assume that the condition of each item is independent of that of each of the other items in the sample. The probability distribution of X, which we have here from the file, is copied in. And then it says A, use simulation to generate 500 values of this random variable X. Okay. Simulation. What we're going to do is down here generate 500 random numbers with a pretty simple function in Excel, rand, parentheses. And what that does is every time we press enter or enter this formula, or actually every time we calculate any formula, every random number is going to be regenerated. It's a 9-decimal number drawn at random between all possible 9-decimal numbers between 0 and 1. And just you can see what happens here as I'll press F2, enter, and every time I do that it'll recalculate. And you'll notice sometimes it's larger, sometimes it's middle, sometimes it's smaller, between 0 and 1. I'm going to do that 500 times. I'm going to copy that down all the way to 522, and that gives me 500. And just to make sure I did that right, I can check with a simple count function. I can count. I'll hit control, I'll hit shift control. Yeah, I've got 500. Cool. Alright. So I've got 500 random numbers. Now, what I want those random numbers to correspond to is a probability up here, and then I can use a VLOOKUP to replace the probability with a number of defectives. So basically I've generated a number that's a probability, and we'll replace it with a number up here. Now, the problem is all my probabilities here are maximum is 0.34 or less, and I've got numbers up here 0.78, 0.5. What am I going to do with them? Well, what I need to do up top is create a cumulative probability function. And to make a lookup table work properly, I'm going to insert a column over here. We're going to call this cumulative probability, cumulative p. And that starts off now at the very bottom, it starts at 0, and then for going up, so for having one or less defectives, we're saying, we're saying for having less than one defective, what's the probability of that? And that equals 0. Okay, so the probability of nothing at all is 0. The probability of less than 1 is simply what we started with, 0, plus the probability of 0 defectives, which is that probability. And if I fill that formula down, what I'll get is a cumulative probability that quickly gets to 1 once we get to the point where where we've exhausted all possibilities. So the only live possibilities for the number of defects are 0 through 7. Okay, and notice that beyond that, there's not a chance of any larger number of defectives. So all possibilities have been exhausted between 0 and 7. Thus, from 8 on, the cumulative probability is 1. So what we're saying here, the cumulative probability is the probability that the number of defectives is 8 or less. Well, because there can only be 7 defectives, that's going to be 1. Same for 9, 10, etc. Okay. Over here, what we're saying is what's the probability of there's one defect is 0.34, but what's the probability that there's 1 or 0? Well, that's 0.34 plus 0.20. That's actually up here because we're doing strictly less than this number of defectives. That's 0.54. Okay. What's the cumulative probability that there's between 0, 1, and 2 defectives? Well, that would be the sum of these 3 probabilities, and that's what we see here. Less than 3, what's the probability of strictly less than 3 defectives? That's these 3 probabilities added up, which is what we have here. Okay, so that's what cumulative probabilities are doing, and now because those are between 0 and 1 inclusive, now we can match those to the random numbers we have down here. And we'll do precisely that with a VLOOKUP table. And next to my random numbers column, I'm going to put in a column called simulated defects. Let's do it like this: simulated number of defects. And what that is going to be is a VLOOKUP that looks up the random number. Whoops, I forgot to say equals. That's why it's not working for me. Equals VLOOKUP. Okay, I'm going to start with that random number. Then I'm going to look up in this array up here where I've got my cumulative probabilities between 0 and 1, and I'm going to replace whatever comes in, and I have to lock my lookup table. I'll get in serious trouble if we don't do that. So put the dollar signs in, and then replace it with whatever in the second column. And I'm just going to fill this all the way down. And now you'll notice that if I have a large number, cumulative probability close to 1, I'm going to get a higher number of simulated defects. If I have a very small number, cumulative probability here, 0.2, it's actually below my threshold value for one defect, so it's going to round it down to 0. Okay, and so on and so forth, 500 trials. Okay, now I have, instead of a probability distribution, I kind of have an actual distribution, if you will, based on that probability distribution, and I can use that to make some calculations about the some averages, some central tendencies of the actual properties of this process. And the only other thing the question asked me to do, okay, so this is A, is B, which is to find the mean and standard deviation, first off, of the simulated number of defects. So we'll calculate mean and standard deviation for them. Well, those are pretty simple to calculate. Let me do some formatting here. Because this is no longer a probability distribution, this is actually a number distribution of discrete values. So the mean is just the average of those values we just generated. And the standard deviation, 1.51. And the standard deviation, now notice that'll change every time I recalculate my random numbers, but it won't get very far from that value. And the standard deviation is a standard dev sample. And the same array here, I can type in the values, or I can do my shift control down and enter. Okay, so there's my estimates, which will change a little bit every time we recalculate for the for my simulation. Now we want to calculate the mean and standard deviation. Let's do that up here of the actual distribution. I'm going to underline this. I'll say the probability distribution. Let's calculate the mean of that and the standard deviation of that. Now the mean of this, remember, because it's a probability distribution, it's not just the average of the values, it's a probability weighted kind of expected value of all the possible outcomes. So it's going to be 0 times 0.20, 1 times 0.34, 2 times 0.26, and all those added up. And the shortcut way to do that, you'll recall, is a sum product function. This array, comma, and then those values times the corresponding cells in this array. Okay, so look, that says based on the probability distribution, my actual mean is 1.5. My simulation is 1.4. Of course, it'll change every time I recalculate. 1.54, 1.5. That's really close to 1.5 exactly. So my simulation is hovering around this expected value based on the probability distribution. And then finally, the standard deviation. Remember this trick. This is where we're using the formula of squaring the outcomes, and then multiplying them by the probability weights, and then subtracting the expected value from that. And that we just did, so that'll be pretty easy. Oh, and then that actually gives us the variance to get the standard deviation. We want to take the square root of that. Actually, I think it'll be clearer if I do this. Let's go ahead and calculate the variance, which equals sum product of the outcomes squared, so I'm going to enter that array twice, times the probability weights, and I'm going to close that down, minus the mean squared. So that's my variance. Now my standard deviation is simply the square root of the variance. Okay, so there's my standard deviation and my mean, and here's my standard deviation and mean for the simulation, and you'll note that they're very close, as we would expect. Okay, we just basically we took this probability distribution and said, let's generate some potential numbers based on it. That's the 500 values we got down here, simulating how many defects this process creates. And then we measured the actual mean and standard deviation of them, and as we should expect, those values are pretty close to the estimated values based on our probability distribution. Okay, so I hope you understand what we're doing with that. It will become clearer, I think, as we move forward in the course, and we'll be generating some more sophisticated simulation models, and we can use, so now we can kind of start putting together all the different components we've learned and build some really useful analytical tools. Okay, so let's do one more problem just to practice this idea of the creating the probability distribution and then simulating actual values with the random variable in the VLOOKUP. And then I think you'll be in good shape to do problem 419 on your own, and that'll wrap us up for chapter 4. So we're looking at problem 420. It says, let x be the number of heads when a fair coin is flipped 4 times. A, find the distribution of x and then use simulation to generate 1,000 values of x. So this looks pretty familiar to things we've already done in the last couple of problems. So I'm going to say x and probability of x first off for my possibilities here. And when I flip a coin 4 times, I can get, it says for the number of heads, I can get 0 heads, 1 head, 2, 3, or 4. Now, to figure out the probabilities, I want to do the same thing I did last time in terms of making a chart of the possible outcomes. So I'm going to think about kind of a tree of outcomes. Flip 1, I can have heads or tails. I'm going to have more stuff in here, so I'm going to give myself some more space. Okay, then on flip 2, based on whatever happened in flip 1, I can have heads or tails, heads or tails. Okay, then flip 3, each of these sprouts off to heads, tails, heads, tails. That's flip 3. And then flip 4, same thing. Sprout off 2 more outcomes for each one. Okay, so there's my tree of all possible outcomes, and let's start off by counting up the possibilities. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so my denominator in my probability calculations is going to be 16. And then I'm going to use my highlighter and kind of strike off the different ways to get 0, 1, 2, 3, and 4 heads. Okay. So let's start with 0. Well, that's going to be the one that's all tails. And there's no other way that gets me all 0 heads, because this tree has heads in it, and those trees all have heads in them. Okay, so that's 1 out of 16. So I can go ahead and write that one down, equals 1 out of 16. Okay, now how do I get 1 head? Well, that's going to be tails, 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 heads. So that's going to be this path here. And every other path has 2. Now there's actually one more. This is tails, 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 heads here. Okay, so there's 2 ways to get that, it looks like. And I'm pretty sure that every other path has 2 heads. Or no, we have one here, tails, tails, heads, tails. Okay, so there's 3. Okay, so I have 3 possibilities there. So that equals 3 over 16. How can I get 2 heads? Let's use a different color and strike off those possibilities. Okay, heads, heads, tails, tails. There's 1. Heads, tails, tails, heads. There's 2. Heads, tails, heads, tails. There's 3. Looking for 2 heads. Tails, tails, heads, heads. There's 4. And then finally tails, heads, tails, heads. I think I'm good. Now tails, heads, heads, tails. So I've got 1, 2, 3, 4, 5, 6 possibilities there. Equals 6 out of 16. How many ways can I get 3? Heads, 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 tails. That's that possibility. Heads, heads, tails, heads. There's 2. Heads, tails, heads, heads. There's 3. Heads, 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 tails. And then finally, how many ways can I get 4 heads? That's heads, 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 and there's only 1. So I'm going to say that's 1 out of 16. Now, to check, make sure I did that right, I want to sum these probabilities. They should equal to 1, right? They don't. I'm missing 1. I'm missing something. That's why I do that check. And if I go over here to where I notched them off, I can see I did miss 1. I missed a tails, tails, heads, tails. So I missed a 1. I missed 1 of my 1 heads outcomes. Okay, so right here, I need to adjust that. I need to add 1 to that. Okay, so that one should now be 4 out of 16. Okay, and that fixed my mistake. And so I'm good to go with my probability distribution. Okay, so the next phase of the problem is to generate 1,000 values of this random variable x. First step is to calculate the cumulative probability, and we're looking at less than this outcome. Well, there's nothing at less than 0. Less than 1, that's simply equal to the previous cumulative probability plus the probability of 0. Okay, and then we can fill that. Okay, so let's set up the simulation. We'll get our random numbers here, and that just equals rand open close parentheses, and it wants us to generate 1,000 values. So we're going to fill this down to all the way down to 1011. Okay, good. So there's my 1,000 random numbers, and now to create a VLOOKUP on the basis of them to replace them with values from up here. To replace them with the corresponding cumulative probability of the different possible outcomes for x. Okay, so I'm now just going to enter my VLOOKUP. I'm looking up the value to the left in A. My table array is up here, but I need to remember to lock in the reference values for the table array. So it's going to be $A, $3, $B, $7 to keep that from sliding when I fill the formula down. I'm replacing with what I find in column 2 of the array, and that should be good. Now that we can fill this all the way down, and now we've got our 1,000 randomly generated outcomes based on the cumulative probability. So that's actually all there is to A. Let me label this A. Now B asks, is the simulated distribution indicative of the given probability distribution? Explain why or why not. Well, here what we want to do is generate a frequency distribution for the simulated values. And what's a frequency distribution? Well, I'll show you. It's very simple here, of simulated outcomes. Okay, and we're going to say outcome, which is number of heads. Okay, that can take the values 0, 1, 2, 3, and 4. The frequency, how many times did that happen in any given simulation? Of course, the simulation's always changing, but we'll have Excel just calculate it based on the most recent one. And that's going to be a count if. It's going to be a simple count if. The range is B12 through B1011, simulated values. And the criteria here is 0, if it comes up 0. Now, before I copy that down, let me lock the reference, at least the rows. Let me lock the rows in that reference, and I can just simply drag that down and change the values. So for 1s, I need to replace the 0 with a 1. For 2s, I need to replace it with a 2. For 3s, with a 3, and then a 4 here. Okay, so based on the most recent random numbers generation adjusted, these are the values I got for the possible outcomes. Okay, almost done. Now we just want to say relative frequency, which is taking the actual count of frequency and turning it into a percent. So that'll just be this value divided by 1,000. And let's fill that for everything. Okay, so now what we're basically, to answer the question whether the simulation is indicative of the given probability distribution, well, let's just compare our relative frequencies to the probability distribution. So is 0.06 close to 0.057? Pretty close. 0.25, 0.256. Yeah, almost right on. 0.375, 0.379, 0.25, 0.253, 0.06, 0.05. I'm going to say that's pretty darn close. Okay, so I'm going to say for answer B, yes, the simulation generated relative frequencies in line with the expected outcomes based on the probability distribution. Okay, and then finally, calculate the mean and standard deviation of the simulated values. How do they compare to the mean and standard deviation of the given probability distribution? Okay, this should be coming familiar to us now. Simulated outcomes, calculate the mean and the standard deviation, and then we'll do the same thing. Let's do it over here, probability distribution. Okay, so my simulated outcomes, that's just the average of the actual values I have in that array, which again is B12 to B1011. My standard deviation is just the standard sample of that same array, B12 to B1011. And then for my probability distribution, my mean is the sum product, or weighted product of the outcomes times their probability weights. Okay, so far looks like that that mean of the simulation is holding up very well compared to the expected value of the probability distribution. Okay, it's within 0.01. Let's calculate our standard deviation of the probability distribution, which is the square root of a sum product product function. And remember, the shortcut formula is to multiply the x outcomes times themselves, and then multiply them times the probability weights, and then from that subtract the mean value squared. Okay, and my standard deviation is also very close to what we would expect based on the probability distribution. So I'm going to say the simulated mean and standard deviation closely match the expected values based on the probability distribution. Okay, so now you're on your own, but I think you should have the tools and knowledge to be able to complete one of these kind of problems. And more importantly, we have the Excel. We have some theoretical knowledge about probabilities and distributions, and some practical knowledge about Excel to have Excel to work with a probability distribution and run a simulation on the basis of that, which, as I've said, is going to be a very powerful tool for us going forward.